I am Bursa. I am a World Heritage Site from the depths of history. I am a depository of civilizations on the foothills of Mount Uludağ. I am the ancient capital of the Ottoman Empire and its enduring spirit. I am Bursa. I am the prayers and calligraphy of the Ulu Mosque. I am the tiles and ceramics that give the Green Mosque its name. I am the houses of worship in Iznik, once home to Romans, Byzantines, Seljuks, and Ottomans. I am the Muradia Mosque complex, where life and death, dreams and reality, poignance and joy are contemplated. I am a boundless land of legends, the living cultural heritage of Jumalı-Kızık, the sun setting on Gölyaza Lake. I am nature's gift to humanity. I am the color green in all its shades. I, a centuries-old sycamore, tones of blue and green, sun and lake, am Bursa. I am the eternal beauty of the Longos forest. I am the rushing waters of the Sai Tabat and Suuçtu Falls. I am a city of flavors, where history meets gastronomy. I am crispy jontic from a wood-fired oven. I am the finest olives and olive oil. I am the birthplace of Bursa kebab. I am köfte with pide and inegern köfte, that is, a paradise of Turkish-style meatballs. I delight palates with sensational flavors, like soft tahini pide and candied chestnuts. I am a land of fresh fruit and nature's bounty. I am paragliding between sky and forest. I am the center for adrenaline and nature sports. I am the timeless shadow puppets, karagöz and hacivat. I am handicrafts at Erganda Bridge, a steel knife forged in fire, a smooth silk shawl from Kozahan, a handcrafted Iznik tile. I am the last stop before Europe on the Silk Road, the covered bazaar. I am so much more than a city. I am Bursa.
Okay, now we continue. Hello everyone again. We invite Professor MAHSEREDJIAN from Polytechnique, Montreal to make a speech. Professor MAHSEREDJIAN is the creator and lead developer of software for the simulation of electromagnetic transients. Now I leave the floor to chairman of the session, Professor Aydogan Ozdemir.
So, good afternoon, everybody. My name is Aydogan Ozdemir. I am from Istanbul Technical University, and I've been one of the organizing committee members of the ELECO. This year, I am really pleased to introduce you our third invited speaker, Professor Jean MAHSEREDJIAN. He was graduated from Polytechnique Montréal with a PhD in 1991. From 1987 to 2004, he worked at Hydro-Québec. It's a research institute in Quebec, Canada, on research and development activities related to the simulation and analysis of electromagnetic transients. On December 2004, he joined the Faculty of Electrical Engineering at Polytechnique Montréal, and he is the creator and lead developer of a software for the simulation of electromagnetic transients known as EMTP. And everybody who are dealing with the power system transients probably know Professor MAHSEREDJIAN very well. It's really our pleasure to see him here as our one of invited speakers. He's going to talk about computation of large-scale power system transients with renewables. As you know, renewables is one of the most popular topics of power system engineers. Probably he will look from the transient sides and from the computational speed and so on. Let me not take more time and give the turn to Professor MAHSEREDJIAN. Yes, please, Professor.
Very much for inviting me to present this work. I am really happy and proud to be participating at LACO conference. So as you already introduced me, here I am just providing my email. You can basically ask me questions afterwards if you have some questions about my presentation. So this is a summary on what I will present. Basically, I will talk a little bit about existing simulation methods. I will talk about data model standardization, portability, interoperability, and some ideas on intelligence in simulations. I will talk about the unified environment for power system simulations, which is a goal that I am trying to achieve. I will talk about advanced interfacing between various simulation tools, about manufacturer model standardization and collaboration with the grid, a couple of slides on that. Then I would like to talk about some other ideas like model documentation, reference, and portability. And perhaps the longest part would be about advanced simulation environments and numerical methods. There will be many research ideas, in fact. So very quickly to introduce, you are all familiar with the classic power system simulation tools. You know that power system engineers, they typically use load flow analysis. Very often these packages are based on the positive sequence network. Of course, this has limitations. It has based on per unit computations. The trend is now to work with multi-phase and balanced load flow solutions, especially when we are dealing with inverter-based resources, IBRs. Distribution networks, as you know, are extremely unbalanced. When we are simulating converters and IBRs, then we have to account for the three phases. There are also short circuit analysis packages, again, based on fundamental frequency, relay coordination tool, and harmonic analysis packages that are based mainly on the injection and propagation of harmonics. You can also deal with harmonic power flow software, which is less common. Regarding transient stability aspect, as you know, the transient stability packages are based on the phasor domain computation. So they assume basically that the network is in quasi-steady state and the network is solved in steady state, let's say at 50 hertz or 60 hertz. The models, they can use differential equations. The numerical time steps are in the range of milliseconds. So this is mainly for slower transients, and everything is assumed to be linear in the network. There are no harmonics. Very difficult for power electronics, okay, because of the switching. So these are not modeled in detail in such kind of approach. Then we are talking about time domain tools, which is the main focus of my presentation. So we are talking about tools for electromagnetic transients. In this case, everything is very accurate. The network equations are solved in time domain. We are dealing what we call with a circuit-based approach. So we can basically model everything very accurately. It includes harmonics. We are trying to imitate what happens when we touch a wire with an oscilloscope. And of course, this is very good for renewables, IBRs, because we can represent very accurately power electronic circuits. Now we are dealing with nanoseconds to milliseconds, or 100 microseconds, 200 microseconds. It can go up to maybe 1 millisecond, but that's really pushing. Typically, these type of computations are for small time steps. Regarding the other methods, you can also represent very accurately power system components using finite element techniques, but these are very slow computations. mainly developed for designing and not for simulating large grids. I mean, designing apparatus. However, we can, from that kind of software, like FEM software, derive circuit equivalents for EMT simulations. And of course, it can be interfaced also if needed, which is not common, but it is a practice that exists in the industry. There are other less common tools, well, maybe more and more used co-simulation methods that I will discuss briefly. Code generation, which is becoming, in fact, more and more popular. I should have maybe not said less common. And DLL-based portable codes between applications are also becoming very popular. Of course, there is another technique or other techniques that are in between phasor domain and time domain. I won't have time today, but I could make a presentation, for example, on the idea of dynamic phasors, which is probably still at the research stage. Then, very quickly, let me just present what I mean by co-simulation. It is very easy. So it means that we have two software packages, could be in the same domain, like EMT Tool 1 and EMT Tool 2, or could be in different domains. EMT means, of course, electromagnetic transients, EMT type simulation. This is not so easy often because you need to develop an interface. So you may have to have transformations back and forth, especially if you are not in the same domain. For example, this could be phasor domain and this could be time domain. You may have to do interpolations if the time steps are not the same. There is a standard called FMI that is very powerful, functional mockup interface that allows to actually interface packages. The network parts are solved separately, for example, in this case, of course, because you have a network part 1 here and network part 2, they are solved and interfaced. Regarding the DLL idea, this is like I said, is very powerful. So you may have a software here and another software, and this software generates code that becomes a DLL, dynamic link library, or it can be just a lib. And then based on that, you are able to encapsulate and take this code that is coming from another package into your own software, okay? This is a very powerful technique. You can, in fact, simulate, for example, very powerful control systems that are in another package, but you have the code of the control system. And it's actually the approach that is being very popular now for manufacturer models. They can provide control systems for inverter-based resources for renewables. So let's go to the computation of electromagnetic transients, the main focus of my presentation. As I already said, they are basically, from practical point of view, there are no particular limitations when we are dealing with such an approach. Of course, it is slower than phasor domain, but it is becoming faster and faster. And also, as you know, there is real time. And, in fact, real time and offline, they are eventually will become probably only one because the computational performance is becoming higher and higher. And offline computations have a lot of luxury, of course, for doing very, very accurate computations. So EMT type tools are very powerful. You can use them for almost anything you want regarding your power system. And as I will discuss in a few minutes, it could become a tool for unifying all environments. So here we are dealing with lightning, switching, electromechanical transients, steady state. And we can also use such a tool, which is circuit-based, for scanning renewables, computing eigenvalues, and performing parametric simulations. Currently, unfortunately, there are no interoperability compatibility standards between EMT type simulation tools. This is an issue in the industry because people use different types of packages, and it's not possible to go from one software to another software. So this is something that I think we should work on and push the industry to adopt some interoperability and compatibility standards. This could be also the same between EMT type and transient stability phasor domain tools. This is complicated. It should be designed in such a way that we could effectively adopt standards that exchange models and topology. And we have to kind of push manufacturers to use those standards. Lack of portability of IBRs and lack of collaboration between different tools is a tremendous bottleneck today in the industry. I think it must be urgently solved to increase engineering productivity and to basically eliminate limitations in simulation analysis of power systems with renewables. There are various efforts. Here I'm providing you a list of efforts. For example, NERC efforts. There is the IEEE standard P1200. There is PNNL, who is submitting inverter dynamic models to the next edition of IEC. Here I made you I gave you other information. And this effort, I think, will continue. Myself, I am very active in this portability and standardization effort. Regarding data model standardization, there are SIGRE efforts that are very good, excellent work for supporting generic models for IBRs. This is my partial list. Again, the generic modeling should be also supported by manufacturers to provide their guidance on the quality on the developed generic models. Of course, the models should be validated by cross-examination, field tests, lab tests, etc. Generic models are very important because before you start integrating renewable energy sources, you have to make some tests and you have to do some planning and analysis, how it will work, how it will perform, what will be the problems, and preliminary analysis of potentially unstable operating conditions when you integrate multiple IBRs. It will also allow you to test your grid codes. It's also very powerful for research and development. So this type of work, as I showed, is being done right now in SIGRE. Regarding the portability of data, I think one powerful approach today is the CIM, Common Information Model Standard. I believe it is the best path today. It provides means for data unification. It can be used to exchange EMT data between software tools. I think we have to work and push that it supports the full spectrum of EMT type models. Currently, it is mostly still kind of phaser domain, but it's improving very rapidly. There are, of course, several complexities. One approach is actually developed by my colleagues at RTE in France, is to use CIM XML files to create a CIM C++ model and then convert it into EMT type C# model and then build automatically. I mean, really automatically, we have to present the schematic. If today to an engineer, you don't present the schematic, it's not powerful. You have to go from the CIM data and build the schematic in your environment so that the engineer can visualize the circuit is going to simulate. So this is already working, and we will continue expanding it, okay? And pushing also EMT type requirements, which are very detailed and complex, into the CIM standard, okay? And of course, ideally, the manufacturer should provide model data according to standards, tests, and parameters. This is an example of EMTP diagram built using that tool. This drawing is built automatically. This is the RTE 225 kV grid after conversion from CIM data. You can also update it automatically from the CIM data if you connect to a database. So then you have your entire diagram and you can simulate the grid. You can integrate renewables. You can basically visualize. It is very powerful if we achieve such portability. I think data model standardization, portability, interoperability should follow by intelligence. So the idea that is proposed here is the fact that perhaps in the near future, we could integrate into EMT type simulation tools a lot of intelligence that will check based on typical analysis methods and guidelines what the engineer is doing. For example, is this normal that the engineer is observing this kind of a voltage given particular data and conditions of the simulated grids? So it is, I think, becoming possible. This is some research idea here. It will be more and more powerful if we provide many support tools and databases for model parameters. model parameters in EMT type environment are complex and they require much more data. So we really need to work on databases. And we also need to work on data calculation tools based on, for example, transformer geometry and tests, line and cable, rotating machine tests. So this can be all, we should push for standardization of all this and availability of information and data to the engineer. So my dream is to basically develop a unified environment for most power system analysis engineering needs. So you will have the same graphical user interface, perhaps I believe based on the EMT computational kernel with some relaxation if needed. And I think this is a trend now. So you would be able to do anything you want. You would be able to do very accurate short circuit analysis with inverter-based resources. You can include protection system details. You can do mechanical transients, electromagnetic transients. And of course, it can be extended to many other types of engineering studies. Perhaps a futuristic vision now, it's already available today, is to basically create some sort of, I call it electronic copy. I claim that I thought about this idea 10 years ago. Now it's called electronic twin. Basically, there are already many examples of this going on in the industry. For example, HVDC projects with converter control replicas. This is done in several utilities. For example, I'm aware of Hydro-Québec in Montreal and RT in France. And you can also connect that to network updating with SCADA. And you can interconnect basically, in fact, whatever you need to perform such simulations. So the future, I think, is very important if you go with EMT. And this slide is just trying to demonstrate to you a case where we have several wind turbines. I'm showing part of a large grid. And there is a case where a fault occurs and the fault is cleared. And then you can see that the fault clearance causes significant decrease in short circuit ratio at the interconnection point of a wind turbine. And if you simulate that using, for example, in this case, EMTP, EMT type tool, and if you simulate it with transient stability package, you don't get the same results. And this is very dangerous because the EMTP tool shows you that you have a major problem. You become unstable, okay? So this slide is to show you how important is EMT type simulation compared to more traditional phaser domain. So I think EMT type simulation is really going to pick up much more, and will become the future for all renewable simulations, okay? To make sure that we have no, for example, instability problems, etc., like shown in this slide. So the electronic copy concept that I just mentioned is presented here. I already explained it, but here, for example, you can have a large grid that is simulated, and on the other side, you could have the live grid. You can, in fact, interconnect the converter replicas and the real converters. You can even upload and download the converter codes. You can send through the computer systems the topology information, settings of protection systems, etc. And this could be eventually, I think, done in real time or offline. This is something that is already available in some places to be able to simulate exactly what is in the field and to even use the physical converter replicas or code. So a slide about advanced interfacing between various simulation environments. This is very important. Like I already told you, there are different types of simulation tools that need to communicate together. Today, the engineer is faced to deal with different tools for his job. And I think we should push that the tools must work in direct interfacing. So it should include capability to perform iterations, derivatives. This is not the case now. Exchange of iterative Norton equivalents between the computation methods, Jacobian matrices, code generation integration. This should include, in fact, low flow solutions, okay? So the model exchange should be very powerful to avoid using complicated tools and procedures for the engineers. This should be fully automated, okay? And it should include, like I said, compliance with all needs, initialization, low flow iterations, etc. Currently, the FMI approach is very powerful, but I think we should push to include all of the above in it. There are already also very good efforts on standardization of code interfaces. The SIGRED B482 is doing excellent work on that aspect regarding, for example, IBRs. There is further work to be done, like I said, about many details when we are dealing with manufacturer models. Here I'm talking about load flow initialization. I'm talking about parametric studies, snapshots, and of course, we now have to do also stability analysis, and the manufacturer models should help us to perform those analyses. The next step would be also to be able to directly connect transparently and very easily the manufacturer models to the actual grid simulator. So this slide is showing the concept which already feasible today. Is basically you can have a grid that is hidden somewhere on a system that is not visible to the manufacturer, but the manufacturer can connect PV or wind turbine models on his own computer, or the organization that is basically dealing with the wind park that has the manufacturer models can do that kind of work. Then they will be, we call them the developers of parks, so they could easily interface through the web and perform simulations and tests while we are seeing the grid in the back, but not accessible to the manufacturers. It is like if they are connecting to the entire grid of the utility. This could be done in several steps. Here I showed you already some ideas. We could also use equivalence if needed, but perhaps everybody now is pushing for more and more accuracy, so this could be done directly using the full grid if needed. Another aspect that is important is model documentation, reference, and portability. I think the traditional approaches for EMT, they are kind of hidden, they are compiled. I think more and more we should push on the documentation of the models and how they are performing and what are the limitations of those models, and provide more information to the user, especially with complicated models such as wind turbines, for example. The increased model contents regarding also the manufacturers, of course, will provide more info to the engineer who is dealing with the integration of renewables. So how we could possibly do that? I think one possibility is to create a model mathematics database. That could be some sort of a system in which the software developers can become compliant in their software package by basically identifying the type of model that they are developing and providing. The same with models from manufacturers. We could also create reference distributor models. One possible approach is to use very high-level modeling languages. One approach that is interesting is the Modelica approach. The Modelica approach, if you are familiar, is an equation-based approach. Here, for example, we are describing a synchronous machine. We are not giving the simulation details and developing very complicated and sophisticated codes like EMTP. We are basically providing at a very high level, and everything else is taken care by the Modelica environment, and it can, of course, automatically also generate code and connect to the EMT solver if needed. So this, for me, is one idea to use model documentation and model portability at a very high level, okay? So, and it could be also multi-domain, because as you know, Modelica is multi-domain, and Modelica supports the FMI approach. So I will give you here an example. I won't go through all the bullets, but basically here is an interesting already test case, use case for model transformation for high-performing grid applications. You can click on this web and you can go and study this project that was done between NYPA, New York Power Authority, and Rensselaer Polytechnique with my colleague Luigi Vanfretti, which we, in this project, they are implementing phasor domain models for Western Electric Coordination Council for renewable energy modeling task force. Okay, so this creates a database of models for benchmarking the translation process in CIM, PSSC package for transient stability, and Modelica. It includes, models that can be used for researchers and developers to verify and compare their work against an established reference. This is a path that has been tested for phasor domain, so we could probably work on this idea when we are working in time domain. In fact, at my university with my PhD students, we developed a library of EMT type models based on Modelica. This is validated against conventional software, of course, in this case, against EMTP. And we have developed synchronous machine models, line models. There are many, many things, including nonlinearities, even complicated models like wideband line models. And we demonstrated that effectively it's possible in Modelica with all the graphical user interface. This is the IEEE 118 benchmark to simulate the grid and compare to EMTP simulations, and the match is very good. We have published papers on this if you are interested. Of course, there is work to do to improve the computational performance of Modelica, but there are many great research ideas in this approach. So I think the advanced simulation environments and numerical methods, for me, the evolution path should go in this direction. I think eventually, like I already mentioned, real-time and offline methods will become only one. We should have the same graphical user interface that is able to do both for very large-scale grids. I think the computational performance will continue to improve, and I think it should be based on the EMT kernel. And modeling accuracy will continue to improve. We should push for availability or more manufacturer test data, IBR standardization, IBR models for manufacturers. Modeling compatibility will improve, modeling standards will improve. And I think the manufacturer should contribute to this effort and provide all the necessary information for the progress of modern grids. So for me, the future is EMT type. Of course, the complexity levels continue to increase. The more we work, the more the needs increase. For example, this is the simulation of a detailed PV park that is really useful in cases where you are looking at faults inside the park or problems regarding the performance of the grid because of some wind turbines tripping or whatever. So it can be very complicated. If you simulate this diagram in EMTP, you have something like 28,000 devices in the entire model. Of course, you cannot use it all the time because it's too powerful and too complex. It includes even the wind park controller details dispatching to individual wind turbines, but you can use aggregated models, okay? So this is the practice today by using per unit based or amplifiers in EMTP, for example, and to provide a very fast model instead of the entire park. However, this is based on the collector grid of the park, as you are probably familiar. If we invent better simulation methods, I just show you the complexity level. There are new needs, so there will be more complex designs. There will be no needs. So I think it will never end, okay? We will continue pushing the limits and establishing more accurate and more powerful packages. So here is a list of better methods for solving circuit differential equations. We have to do research on better numerical integration methods. We already worked on variable time step. Apparently, there is some feature in it if it is efficiently implemented. We should work on model relaxation and adaptation according to the numerical integration time step. We should look into better formulations. The formulation that I developed is called modified augmented nodal analysis. It is already powerful, but we should go further, especially if we want to develop the powerful environments that I just showed you, okay? And I believe that everything should be very accurate. We should use iterations. And it should be very fast to adapt. And we should also use, of course, more and more parallel computations. So here is in the case of EMTP, my baby, basically the computation methods main blocks. Very important in EMTP, it's possible to basically use the log flow of the grid that we have on the screen and to find the steady state solution on constraints in the log flow to initialize and then to move to the time domain simulation. The modified augmented nodal analysis approach is kind of summarized here. As you know, right now, most EMT type packages are based on the idea of trapezoidal integration. And in EMTP, we also have backward Euler discretization. So the devices like capacitors and inductances become an equivalent resistive circuit with history terms. In my case, I'm using this formulation, sparse matrices, non-symmetric, and of course, we can include the classic nodal admittance matrix, but it is surrounded with augmented mathematics that allow to do much more powerful things compared to classic nodal analysis. Here is a view, an expanded view. The ordering is just for symbolic presentation. You can enter the equations in any way you want. So basically, you can, in fact, evacuate nonlinear functions. This is powerful if you want to update your matrix very fast. So you can evacuate also the rotating machines into the augmented portion. The voltage sources are augmented. The dependent branch relations are evacuated. You basically have, for example, here the model of an ideal transformer. This could be many other dependent and control sources. Ideal switches, you can model very, very quickly. You don't need to collapse a column and a row in Y matrix when you are modeling switches. This is much more powerful, okay? But you are seeing only a part of the power of this approach. There is much more actually that can be demonstrated, but further research is still needed. The same is used in MTP for doing log flow. It is a bit heavy, this slide, but basically we keep the same circuit-based approach. No need to use per unit, in fact, because in EMT type package, you cannot use per unit computations, okay? So you need a log flow that works in ABC or any phase numbers, in fact, because in EMTP, you may have many, many wires, right? And you basically keep the exact copy of the circuit that you are simulating, but you augment it with constraints. And if you augment it with such constraints, now you can add converter controls for IBRs, load constraints, classic generator constraints, Thevenin equivalents for converters, for synchronous machines, for asynchronous machines. And it is much more generic, much easier to formulate, and much closer to the reality of an EMT type simulation and the actual power system than the classic mismatch equations that you are familiar with. This is actually much easier to formulate, okay? And I'm working very hard to demonstrate to everybody that we should abandon using the classic mismatch equations when we are dealing with multi-phase low flow, unbalanced low flow simulations. So, and this can directly initialize time domain equations in EMTP, actually. It can be applied to islanded microgrids, AC-DC microgrids. If you are dealing with AC-DC microgrids, all you need to do is to take this formulation for the individual AC microgrids, for the DC microgrids, and provide the coupling between them. This is the Jacobian matrix of the interlinking converter. So, of course, it's based on Newton iterations. So automatic initialization is extremely important, okay? Not only it saves computing time, but if you don't initialize correctly, you may end up into the wrong solution field, okay? You really have to make sure that everything is below the given constraints and following the constraints that you are providing for your inverter-based resources or classic synchronous machines. Here I am showing a classic test case of 230 kV. It includes all the controls, of course, the exciters, governors. Here I'm just showing you the governor. One of the problems is to initialize the controls. It is feasible today in EMTP, for example, to propagate backwards what should be the output and to initialize all the history terms, for example, using the limit theorem by making basically S go to 0. It is feasible, but some rules have to be implemented. Fully automatic is a research that is ongoing right now. So here is without proper initialization. Of course, the system starts and it takes forever. After 5 seconds, it's still ringing, you know, it's still doing crazy things. And as I said, be careful. It may end up into the wrong solution. And here is with low flow initialization, perfect initialization. Of course, the system is unbalanced, so you don't have a straight line for the power. This is the power, okay, machine power. So this is the demonstration of a fault of an electromechanical transient. You can see we start with perfect initialization and we can apply the study immediately. We don't have to wait. And then we can change anything we want and we can do the simulation again without waiting. So it becomes really complicated when we start dealing with IBRs. For example, in this case, we have a PV park. It will be very complicated because now it includes electronics, it includes very complicated controls, but it's feasible. It is basically, in this case, the encapsulation of the initialization procedure. So these are the input data for the PV park in EMTP. So you have to specify, of course, the controls. You have to also select the type of model you want for the converters. You can go with average models in many cases because you can use a larger numerical integration time step. Or if you want more details, then you can go with IGBT detailed converter models. As you can see, it's very complicated, okay? So this is the sub-circuit of the model. You have the converter controls, you have actually the PV panel, you have the hardware here, and then you have the the PPC, and then you have the initialization procedure being implemented, which is working with the low flow. Okay, so the idea is that this is a basic simple trick, but it works very well. The idea is that you provide the low flow constraint using an ideal voltage source initially. The low flow constraint depends on the control that you are putting in the top panel of the PV for the park or for the individual PV if you want. And basically that will initially be connected to the grid as an ideal voltage source and connected to the PV as an ideal voltage source, so that the PV will not see the grid for a few seconds. Here it's 0.2, but it is actually, you can set this, it could be below 100 milliseconds. And at that time, it is able to initialize much faster. Of course, we also provide the initialization to internal components like controls to start it very fast. And then it starts, and then you basically disconnect the ideal voltage source, and the PV becomes now connected to the grid. So it shows to you that here, in this case, we are doing a fault on that grid that we showed. It shows to you that we are initialized below 100 milli here, okay? Of course, at the beginning, it takes some time, like I showed you, because we are not connected to the grid with the PV. We are dealing with an ideal voltage source. We trip it off, and then you can apply your fault very quickly. So in this case, the fault is applied at 200 milliseconds. So it's feasible to do this kind of sophisticated initialization in EMT type simulator, EMTP in this case. So now let's talk a little bit about fast computations. So you can do basically fast computations. I think that's the future, using full circuit-based EMT simulations. You can also do combined computations, etc. I am not sure, because it's not easy to automate and generalize when you are combining, for example, phasor domain for parts of the grid and EMT. You can also use concatenation methods, but all of these are really not easy to generalize. This is easy. It's on your GUI, you just push start and that's it. And you don't really care about intervening as a user, okay? Of course, there's other ideas, for example, dynamic phasors. My experience is that dynamic phasors become very slow when you compare to EMT type approach, if you have an iterative solver in the EMT type approach, because in EMTP, for example, we can iterate, and then when we increase the time step up to 1 milli even for doing slow transients, it does not explode numerically because of the iterations, okay? In this case, dynamic phasors is not being advantageous, okay? So fast computations can be performed, of course, offline and real time. As you know, today we are parallelizing using delay-based decoupling, okay? This can be done using topology recognition or can be done by the user by cutting. I am just showing you a few ideas here. So the separate blocks can be found from network automatically using line delays, and there is no error here. There is no user intervention. There is a package called KLU, which is probably currently the most efficient approach for the sparse matrices. The issue often in these problems is the fact that when you have power electronics for IBRs, they change the matrix, so you must refactorize, okay? So the same for nonlinear devices. So it slows things down, and many theories that we develop do not perform because of these issues. So, however, as we worked on some ideas, which is called the parallel KLU solver, which is called SMP EMT2, It uses what we call pivot validity testing that is explained here, and partial refactorization. The idea of partial refactorization is the following. You have your matrix and you have switching components. If you are lucky, they are located at the rightmost of the matrix, and you are able to restart your ALU decomposition from that point instead of doing it continuously. It saves computing time. Here is an experience case with the Hydro-Québec grid. I won't go through this, but you can see that this is a monster grid with almost 30,000 nodes. You can see that it's full of nonlinearities. It iterates per time point in average 2 times. And this is the grid sparse matrix. Then you perform BTF transformation to make it block diagonal. And by doing a block diagonal matrix, you are able to automatically separate and simulate on different cores. These are the gains compared to the classic EMTP solver on one core. The KU even is not faster than the sparse matrix package that I'm using. And then this is the new approach. As you can see, the gain are significant. This effort was already published, but since then we improved, and shortly I will be able to report on more gains in computations in parallel. When you go to large grids like this one with renewables, it becomes more complicated because you have all these converter equations, all these controls. You have average value models, or you can use the detailed ones. Of course, detailed ones requires time step like 10 microseconds because you are dealing with nonlinear IGBTs. If you simulate this, again, it's quite big. Of course, it's not as big as the Hydro-Québec grid, but it's full of nonlinearities. So now your iterations are very high, okay? But it reduces, of course, if you go with the average value model. In this case, this is a test case that basically demonstrates the wind turbine powers after fault analysis. As you can see, again, initialization is very quick, okay, and the simulation of the fault is at 1 second. These are the performance timings. The gain with DM is very good, and the gain with AVM is not as excellent because AVM already is fast, but still you have those gains. This is the modified KLU that I showed you. And these numbers have already been improved by further research. There are other parallelization techniques when you don't have the line delay propagation. The technique is basically based on combining mana and state space, or null analysis if you prefer, but mana is more powerful. So the idea is that pieces of the grid are simulated in state space and pieces in mana. So, well, I won't go to the details of the mathematics, but basically the branch equation of the state space equation becomes directly integrated into the mana. This is the network equation, the full network equation, sub-network equation. And this is a typical application example that you can find in our research. If you have such a case and you try to simulate in real time, you may have to save a huge number of combinations, which is not a good idea. You may exceed, in fact, the memory of the computer, even if you have the most powerful computer. But with this approach, you can really cut and separate in these arbitrary locations. You can do it manually, and then you can achieve the computation of this very efficiently with the SSN approach. There is another technique called the compensation method. It is not well understood in the literature. It is, in fact, related to many other techniques that people publish, but this technique was invented much before, and it's extremely powerful. It allows you to cut anywhere. In fact, it allows you to cut through wires, okay? So without going into the details, the idea of the compensation technique is that you separate through wires, you simulate the network separately, and then you compensate them with, by providing the effect of the wire currents or the branch currents, okay? So cutting through wires with compensation technique is very powerful. Of course, the difficulty, again, is the reformulation of the matrices. In the compensation technique, you will have to use a Thevenin equivalent of the grid at the given simulation time point and iteration, okay? So this is allowing you to move from the decoupled matrices to transmission lines to border block diagonal matrices, okay? So without spending too much time, you can find the border block diagonal matrices automatically by using different techniques for like METIS. In this case, in mana, it's very powerful because we already have the notion of ideal closed switches, which are the wires. The procedure is somehow illustrated here. It's not so complicated in the sense the idea is that you solve initially the grid separately, then you find the combined version current, and you use this current to compensate the solutions of the individual grids, and you find the final solution. This slide is showing that you can, in fact, parallelize the procedure for LU factorization. The trouble is when you make changes because of power electronics in the matrices, okay? Otherwise, this is kind of academic because basically it doesn't give you the gains that you are thinking you will get because you have to refactorize those matrices. But still, there are many ideas here. Now, advanced simulation environments and numerical methods. Let's go to other ideas that I already discussed. Should we use high-level programming and abandon old software development approach? I don't know. There is a lot of research to do. In addition to Modelica, there is another language that I'm working on. It's called Julia. It is very powerful to deal with such methods. They are kind of slow today, but I think with research, we can improve them, or we can develop a kernel that is doing mathematics and connecting models, which has already been done also in our research with Modelica. We have to continue working on the log flow. As I showed you, there are a lot of work to do, especially with converters. There is a lot of research to integrate the converter controls. I already showed you that it's feasible with the current formulation that we have. There is still other work to do with power electronics because the power electronics, they switch, and to be able to have very accurate IBR models from the log flow solution, we have to account for control options, like I already said. We have to push research on automatic initialization of controls and circuits. Already, I demonstrated to you that there are several capabilities available today, but there is still more research to do. Accurate switching, variable time step are research ideas, research trends that are still very active regarding power electronics and fast computational power electronics because of massive IBRs. Analysis detection methods for determining unstable conditions are very powerful in EMT type environment. There are perturbation techniques, parametric analysis. So this is also very advanced. We have to basically push the user accessibility to EMT type models. And I already gave several ideas about the fact that we need more data. We have to provide database. We have to simplify the tasks for performing simulations and studying results. There is a lot of development to be done in this field. And the user should not basically do anything else than push run and should not adjust for internal solution procedures or for limitations. I am giving you here the specific example of line and cable models. Although we have achieved very advanced levels of very accurate modeling of lines and cables, but still there is research to be done regarding, for example, passivity issues that are annoying. It's very complicated, and the more powerful you make the tool, the more complicated systems the users will build, and you will need more research to cope with that. FDNE approach that I kind of discussed, the idea is to accelerate computations by cutting anywhere you want. This is feasible today. However, you have to deal with different things, the presence of nonlinearities. You may again have passivity violations, although this research is becoming much more mature, but still, these are very various complexities that should be also automated, okay? Load models, I think for the power system engineer, the model of the load is very important. Here is some research done with Hydro-Québec regarding load modeling and trying to reproduce transient events in a hospital using what we call component-based models in MTP. It's feasible, but you require a lot of data. And in fact, the idea would be achieving an approximate model based on generic knowledge, intelligence that we can continue to push, work, and provide. I think we have to push benchmarking for testing and comparing IBR models and numerical techniques. I already mentioned this. Please also, we have to work on the test cases to be able to demonstrate various power system problems and also compare, models, etc. There is already some work available. You can go and search for the Seagrave brochure 736. So the futuristic vision for me, I'm approaching to the end of the presentation, is basically an adaptive and super fast simulation. Simulation results adapt to changes on the screen automatically. It is kind of, if we had the exact grid on our computer, we touch anything anywhere and everything changes automatically. Of course, we have to use the new resources, clouds, web access for manipulating data, GPS, advanced visualization tools to guide the engineer in what is being done. The needs will become more and more complex with IBRs. So here is, for example, a futuristic vision. Let's say the grid is live on my computer, so I can touch anything I want on the screen, and it will automatically respond with the corresponding transient. To achieve this, we need a lot of research, okay? But, it can be partially done today, but to be able to touch anything anywhere, similar to a transient network analyzer like in the old days, this requires much for research for reformulating the equations for the numerical computations, computational speed, etc. So advanced EMP GUI, the graphical user interface, is a fundamental key component in the simulation of transients. This is the EMTP GUI for distribution grid, IEEE 8500 benchmark. You cannot draw this manually. It will take too much time. Even if you have 20 students like me, you really need to be able to have the automatic drawing on the screen using GPS coordinates, and then you should be able to zoom and view it like when we do with Google Map, okay? This is the dream. Right now, we can at least draw it automatically with GPS coordinates, but then we need to implement tools that allow us to have layers to visualize the level of details that we want to achieve. In conclusion, modern power system tools rely on power system simulation and analysis tools. Modern power system simulations. The electromagnetic transient computations are circuit-based. I think they offer the best potential for expanding into various applications today. The new simulation needs should favor the EMT approach. I insisted on this many times in my presentation. EMT tools today exist and they are powerful, and major technological advances have been already made, but we have to conduct much more further research for the next generation of tools. There is an important aspect, which is the graphical user interface. It is a very, very important aspect because you can do very nice mathematics, but if you don't have a powerful graphical user interface, then it's useless. And we have to work very powerful, very, very much on data and model standardization, which are key factors for the progress of studies of IBRs, renewables, so database, manufacturer models. So this concludes my presentation. Thank you very much for listening to me, and I hope it was not too long.
Thank you very much, Professor, for this very valuable and interesting presentation. I will be really waiting for the future vision, especially adding the intelligence to your simulations. It will be very attractive, I think so. And our time is about to finish. So, as Professor mentioned, one of the most time-consuming part in our power system analysis is the transient analysis. And he's an expert in this area. But unfortunately, we didn't have more time for the questions. We will leave it. You can ask your questions through an email, probably. Is
Please,
it okay?
I have provided my email. Yeah.
That's good. Once again, I would, on behalf of organizing committee, I would like to thank you for your presentation and for your collaboration. Thank you very much, Professor MAHSEREDJIAN, and hope to meet in face-to-face activities in the future.
Thank you very much. It was an honor. Thank you very much.
Thank you. Thank you.
We would like to thank esteemed Professor Dr. Mr. MAHSEREDJIAN for the valuable information he gave in the presentation. We would also like to thank him for his efforts and joining us despite the big time difference in these difficult conditions. And thanks to dear Professor Aydogan Ozdemir for his contributions and helps for all day. Dear participant and guests, I hope the first day is going well for all of you. Our conference will continue with the Zoom seasons, and this is how we will end the day. We are going to continue with the seasons tomorrow morning, and we'll start at 10 o'clock. Also, in tomorrow, there are 3 distinguished invited speakers make presentations about valuable and beneficial topics. For season links and detailed conference program, please visit www.eleco.org.tr. We are ending our live broadcast for today. See you in tomorrow's live broadcast. Have a healthy and good day.
Crafted with a great effort for centuries in Bursa of Bursa. Bursa Silk. Bursa, the Grand City.